breakthrough projects. In this video, we are going to explain about the project entitled as Identification of Earthquake Precursors, Origin, and AI Framework for Automatic Classification for one of these precursors. So before getting into the video, let me give you a brief description about the project. This work investigates the origin and underlying mechanisms of earthquake precursors and proposes an AI-based framework to automatically identify and classify one specific precursor. The approach aims to improve early warning systems by combining geophysical analysis with machine learning techniques. Coming to the abstract states that earthquake prediction is difficult because seismic activity is highly complex and unpredictable, but scientists have identified certain unusual signals such as change in ground deformation, radon gas levels, electromagnetic activity, ionosphere variations, and acoustic patterns. They may appear before an earthquake. These signals are known as earthquake precursors. This project selects one specific precursor and develops an AI-based system to automatically detect it using machine learning and deep learning methods. By combining real-time sensor data, feature extraction techniques, and predictive models, the system aims to improve the accuracy of precursor identification and provide a smarter decision support tool for early earthquake warning applications. Coming to the existing system states that earthquake monitoring system mainly uses traditional tools like seismographs, GPS measurements, and manual analysis to identify possible warning signals. While these methods are useful, they often have difficult reliable detection, non-seismic precursors, and cannot easily handle noise sensor data or large complex data sets in real time. Traditional statistical techniques used in this system are not very flexible and struggles to capture the nonlinear patterns found in earthquake-related signals. As a result, the accuracy of precursor detection is limited, and important anomalies may be identified too late. Coming to the proposed system or base paper work. The proposed system uses an AI-based approach to automatically detect and classify a chosen earthquake precursor, such as electromagnetic changes, radon variations, or ground deformation patterns. It applies advanced pre-processing, feature extraction, and machine learning or deep learning models like CNNs, LSTMs, or hybrid networks to accurately identify anomaly patterns. With real-time data processing, automated model training, and sophisticated anomaly detection techniques, the system can recognize weak or complex signals that may appear before an earthquake. Overall, it is designed to be scalable, adaptive, and more reliable than traditional or manual detection methods, offering improved support for early warning applications. Coming to the dataset, the earthquake precursor dataset from Kaggle contains sensor-driven numerical features meant for machine learning studies on detecting potential earthquake warning signals. Although it lacks official documentation or a clear data dictionary, the dataset generally consists of time series-based attributes that describes how precursor signals behave before seismic events. This features includes basic statistical measures such as mean, standard deviation, skewness, and kurtosis, as well as signal strength indicators like RMS and energy that reflect the intensity of the recorded activity. It also provides dynamic features such as slope, trend strength, and peak counts, which capture changes in the signal over time. Additionally, frequency domain features such as spectral centroid, spectral bandwidth, and entropy offers insights into how the signal distributes across various frequencies. A sampling rated field indicates how quickly the data was originally collected, while a label attribute classifies each entry as either a precursor or non-precursor instance. While the dataset is suitable for experimental and developing AI-based classification models, it lacks of metadata and verified sources, means It should be used primarily for academic or exploratory purposes. Coming to the novelty or extension or enhancement or improvement. The extensions introduced in this project significantly enhance both the predictive performance and practical usability of the system. First, advanced deep learning and ensemble techniques were integrated to improve classification accuracy beyond the baseline CNN model. By implementing a stacking ensemble where multiple models work together to make a final prediction, the system achieved a noticeable accuracy of 99.6%. Further, improvement was realized through a BLSTM architecture, which is especially effective for time series data because it captures both forward and backward temporal dependencies. This model achieved an even higher accuracy of 99.8%, demonstrating its superior ability to learn complex precursor patterns. To make the system more transparent, explainable AI methods such as line were applied to interpret model prediction by highlighting which features contribute most to each classification. This ensures the system is not only accurate but also trustworthy and interpretable. Finally, a user-friendly interface was developed using the Flask framework, allowing users to input data and obtain predictions from the trained model in real time. This extension transforms the project from a purely experimental system into a practical, interactive tool suitable for real-world use. Coming to the flow of the work, firstly, importing the packages. This module loads all the necessary Python libraries for data handling, visualization, machine learning, deep learning, and model evaluation. It prepares the environment so all further steps can run smoothly. Next, exploring the dataset. The dataset is loaded and checked for shape, missing values, feature types, and class distribution. This helps understand the data structure and identify if any cleaning or pre-processing is needed before modeling. Next, data visualization. Visual graphs are created to better understand the data. Trend strength distribution shows how the trend strength feature is spread across the samples. The correlation matrix displays relationship between features to see which one are strongly correlated. These visual guide feature selection and pre-processing decisions. Next, splitting the data. The dataset is divided into training and testing samples. The training set is used to build models and the testing set is used to measure performance on unseen data. Next, building classification models. Multiple machine learning and deep learning models are created to compare the performance. Next, training the model. Each model is trained using the training data set. During training, the model learns patterns that help it classify precursor or non-precursor signals. Next, we have model comparison. All trained models are evaluated using common performance metrics. This helps identify which model performs best overall. Next, we have the comparison of graphs. Graphs are created to visualize, compare model performance. These helps quickly understand which model achieved the highest scores. Next, save the trained model. The top performing model is saved using pickle or joblib, so it can be used later for prediction without retraining. Next, explainable AI visualizations. Techniques like line are used to show which features influence model predictions. This increases transparency and trust in system. Coming to the front end, a user interface is created using Flask. It includes user registration and login features with SQL database support. The UI allows users to enter feature values manually for prediction. The entered values are cleaned, scaled, and prepared to match the format expected by the trained model. The saved best model is loaded and used to generate predictions based on the user's input. The prediction results, like precursor or non-precursor, is shown on the front end in a user-friendly format. The algorithms used in the project are random forest, decision tree, naive Bayes, logistic regression, KNN, SVM, XGBoost, voting classifier, and CNN is trained by splitting 60 is to 40%, 80 is to 20%, and 95 is to 5%. And as an extinction, we use stacking classifier and by LSTM. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements, application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. To execute this project, first, we need to open the code folder, which contains the project source code files. This folder is a complete package of your project's code base, containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing users' requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project's code during the runtime. Notebook.ipynb files. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store user information. Now, coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with a port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. This is the home page of the project should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have home button and sign up button. Now, click on sign up button so that the log on HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and the login.html will be opened, where you need to access the application by username and password. Then click on login so that the prediction page has been displayed. In this, we have predict precursors button, data analytic button, notebook button, and sign out button. Firstly, click on predict precursors button so that the precursors classification prediction form will be opened, where we need to give the input values and predict the output. Here, by giving the input values, we must find out whether the given inputs are precursor or non-precursor. Firstly, the mean value will be 0.330981. The standard deviation value will be 0.237286. Squeeness value will be 0.937715. Kurtosis value will be minus 0.12. RMS value will be 0.407251. Slope value will be 0.000755. The trend strength value will be 0.9180491515. Spectral centroid value will be 9.004114,231. Spectral bandwidth value will be 8.005020,692. Number of peaks value will be 319. Mean peak height value will be 0.374793,022. Energy value will be 165.8531. Sampling rate value will be 50. Now click on predict precursor classification so that the input values are pre-processed and the output is displayed as precursor detected, and the analysis was completed on 12/4/2025 and time is also being displayed here. And we also have the classification metrics that it's very high, it's active and required. We also have the detailed analysis and recommendations like what are the immediate actions, safety information and the recommendations. We also have the next step. Now click on make another prediction so that the form will be open again where we need to give the input values. As of now, we detected the precursor detection. And now let us check the values for precursor not detected. The mean value will be 0.64102. Standard deviation value will be 0.20061. Skewness value will be minus 0.80283. Kurtosis value will be 0.653381. RMS value will be 0.671677. Slope value will be minus 0.00047. Trend strength value will be minus 0.676289415. Spectral centroid value will be 0.96422258. Spectral bandwidth value will be 3.137455,816. Number of peaks value will be 250. Mean peak height value will be 0.666924937. Energy value will be 451.1503. Sampling rate value will be 100. Now click on predict precursor classification. So it is detected as normal activity confirmed, which means it is a non-precursor detection. And the analysis completed on 12/4/2025 and the time is also given. We also have the classification metrics like low, stable, routine. And the detailed analysis recommendation is recommended actions, safety status, recommendations and next steps. Now click on view analytics dashboard so that the visualization and performance metrics will be displayed. So firstly, let us check with distribution analysis. First, we have slope distribution graph. This graph illustrates the distribution of the slope features for ramping and non-ramping signals. The non-ramping class label is 0 is centered around a slope value close to 0, indicating that these signals generally show little or non-upward downward trend. It constrains the ramp class is clearly shifted towards positive slope values, showing the precursor-like signals tend to have a stronger increasing trend. The graph illustrates the distribution of the slope features for ramping and non-ramping signals. The non-ramping class is centered around a slope value close to 0, indicating that these signals generally show little or no upward or downward trend. In contrast, the ramping class is clearly shifted towards positive slope values, showing the precursor-like signals tend to have a stronger increasing trend. This separation between the two curves highlights the slope is an important and discriminative feature for distinguish between precursor or non-precursor patterns. Next, we have trend strength distribution graph. The graph shows the distribution of trend strength of ramping and non-ramping signals. Non-ramping signals are mostly centered around 0, indicating weak or no consistent trend in their behavior. In contrast, ramping signals are heavily concentrated near a trend strength of 1.0, showing a strong and stable upward trend. This clear separation between the two distributions demonstrate that trend strength is a highly discriminative feature, making it very useful for distinguish precursor like ramping behavior or from normal non-ramping patterns. Next, we have correlation and classification analysis graph. First, we have correlation matrix graph. The correlation matrix visualize how different features in the dataset are related to each other and to the target label. Strong positive correlation appears in warm colors, while strong negative correlation appears in cool colors. Features such as mean, RMS, mean peak height, and energy shows strong positive or negative correlations with the label, indicating their importance in distinguish precursor and non-precursor signals. The matrix also highlights pair of features that are highly correlated with each other. For example, spectral centroid and spectral bandwidth, suggesting redundancy. Overall, this graph helps identifying influential features and guides feature selection for building effective prediction models. Next, we have confusion matrix. The graph is a confusion matrix representing the performance of a classification model distinguished between no ramping and ramping. The model correctly predicted 837 insanes as no ramping and 360 insanes as ramping, while misclassifying 3 no ramping instance as ramping and none of the ramping instances as no ramping. This indicates the model has very high accuracy and performs slightly better at identifying ramping instances without false negative, with only a minimal number of false positive for ramping. Overall, the model demonstrates strong predictive capability for both classes. Next, we have model performance metrics graph. First, we have the accuracy graph. The bar chart compares the accuracy of different machine learning models on a specific task. Traditional models like random forest, decision tree, KNN, SVM, and XGBoost shows high accuracy, with voting classifier and stacking extensions perform slightly better. CNN models achieve moderately accuracy, which decreases as the dataset splits into 60%, 80%, and 90%, while the extension by LSTM model achieves the highest accuracy among all models. Overall, ensemble and advanced neural network models outperform standard classifiers. Next, we have precision graph. The bar chart displays the precision of different machine learning models. Most models include random forest, decision tree, KNN, and XGBoost, achieving highest precision close to 1.0. CNN performs various with dropout rates, with CNN 95 shows notably lower precision. The extinction by LSTM model achieves the highest precision among all the models. Next, we have recall graph. This bar chart displays the recall scores of various machine learning models. Most models include random forest, decision tree, KNN, and XGBoost, achieve high recall close to 1.0. CNN model shows a decrease in recall as the dropout rate increases, with CNN 90% performing the worst. The extinction by LSTM model achieves the highest recall among all the models. Next, we have F1 score graph. The bar chart shows the F1 score of different machine learning models. Most models include random forest, decision tree, KNN, XGBoost, SVM, and ensemble methods, performing very well with F1 scores close to 1. CNN model shows decreasing performance as the confidence threshold increases with CNN 95% performing the worst. The extinction by LSTM model achieves the highest FN score among all models, indicating the best overall performance. Next, we have ROC and AUC accuracy graph. The bar chart compares the ROC and AUC scores of various machine learning models. All models achieve very high performance with scores close to 1.0, indicating excellent classification ability. Traditional ML models, ensemble models, and neural network extinctions perform similarly with only slight variations among them. And we have explainable AI SHAP analysis graph. This SHAP summary plot shows how each feature contributes to the model's prediction. Feature at the top has the strongest influence while those at the bottom matters less. Each point represents one sample with color indicating whether the feature value is high or low. Points to the right increase the model output, with those to the left decrease it. And then click on sign out. So finally, the project successfully identifies key earthquake precursors and analyze their origin to better understanding their significance in early warning systems. An AI-based classification framework was developed to automatically detect one selected precursor with high accuracy. The results demonstrate that integrating precursor analysis with machine learning can greatly enhance the reliability and speed of earthquake prediction. Overall, this study provides a strong foundation for future improvements in automated seismic monitoring and early warning technologies. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.